This video will discuss the solution to question 34. Consider the SR latch in figure 6. Let it have its metastable point at Vm is VDD over 2 and ignore the channel length modulation of the MOSFETs. What is the minimum width that each of the identical transistors Q5, Q6, Q7 and Q8 must have so that switching occurs when setting or resetting the latch if the aspect ratio of transistor 1 is 2? And then 8 possible widths are given for these 4 transistors. In order for this switch to be able to change the state of the latch, we should impose a constraint on the currents that can be pulled by these 2 transistors collectively. The current in this case that can be pulled by transistor 5 and 6 should be larger than or equal to the current that can be pulled by transistor 1. And we will deal with transistor 5 and 6 as if they are one big transistor with double the channel length because they are connected directly to each other. Let's say that the latch is in a state where this node has a high voltage. If this transistor or transistor Q5 and 6 would start to conduct, that means that the drain to source voltage would be very high with respect to the gate source voltage. So provided that Q1 or Q5-6 would be turned on, both transistors would be in saturation mode. That means that this constraint is equivalent to saying that the aspect ratio of the big transistor created by connecting these 2 to each other would have to be larger than the aspect ratio of transistor 1. The aspect ratio of transistor 1 has been given and that value is 2. That was in the question statement. So from this we know that the width of our big transistor 5 and 6 would have to be larger than 2 times the length of the channel of our transistor 5 and 6. But this length of the channel of these 2 transistors in series would be just twice the length of the channel of a single transistor. So that's 2 times 40 nanometers. 2 times 40 nanometers. And that is the same as 160 nanometers. So in other words, the width of this transistor has to be larger than or equal to 160 nanometers. Transistors Q5 and Q6 are directly connected to each other, so we can act as if this were one big transistor with double the channel length, since this is the length of transistor 5 and this is the length of transistor 6. The width is into the screen, so that would be, and that width does not change if we were to double the length. So that's an important thing to remember. The width does not depend on chaining these to each other. And this means that the width of transistor 5, but also the width of transistor 6 and transistor 7 and transistor 8 all have to be 160 nanometers.